Good. Oops. All right, congrats. Let's see Vivian and Leonardo. Congratulations. Yeah, I don't know who you are, but congrats. So we're gonna go over the questions. Let's see. First one. Okay, here we go. So you want to block the inside of a door from zombies with a heavy barrel. Where should you place the barrel? And you should place it closest to the doorknob. All right. So this isn't going to be a very scientific explanation, all right? But it goes something like this, right? So if you imagine like from a top-down perspective, right? You have your door. And that's the hinge of the door, right? It's on a like pinned support, kind of. And then you have your barrel. So it's like that, right? That's like the doorknob or whatever. I don't know what this drawing is. I'm sorry. Yeah, basically, because this barrel's on the side furthest away from the hinge, it's going to require like a greater moment than over here because the lever arm is bigger. Yeah, so this is just kind of like you'll dip your toes into what moments and stuff are all about, and I'll explain that better than this in a bit, but that's kind of the idea, right? So the next question. That was just like a fun little sci-fi one. I don't know why I did that too much. Yeah. Okay. So the sine and cosine rule, right? This is what I was showing a little bit of earlier in the lectures. So yeah, essentially you want to use these when it's not a right angle triangle. And that's kind of where the other answers are wrong, because for those ones, including like when you have a vector and you know its x and y components, well, it can be represented as a right angle triangle, right? So yeah, sine and cosine rule will be useful when it's not. So I'll give you an example. Something like this. Or yeah, like this triangle here. Yeah, it's useful then. Right. So a fixed support, right? So supports were covered in today's lecture. And there's basically 3 types. Right. Let me go over to Discord. Yeah. Here's your roller support. Here's your sorry. This one's your pin support. And this one, which kind of looks like a wall, is your fixed support, right? So there's variations on these. Like, I'll give you an example. I think last workshop, we saw like the slider, which looked like this, where it was free to slide up and down like this, but resisted in this direction, like the normal forces resisted. And that's pretty much what a roller support is. So it only resists the normal force direction, but it's free to move in the tangential direction like that. A pin support, it's resisted in both the tangential and normal directions, right? And a fixed support is resisted in tangential, normal directions, and it resists its I should point it that way. It's also resists rotation, right? So let me go over to. Sorry to the people copying this down. I'll come back to this in a second. Okay, so an office stapler, right? It doesn't resist rotation, right? That's assuming that the stapler is even, I guess, like heavy enough to resist any loads, because it's just something on a desk, right? But like, yeah, so it's got a hinge, and so I would consider that maybe like pin support or something. Yeah. House of cards. So
Hey Henry, you're on mute.
oh my goodness, what's going on? Okay. Sorry, it keeps muting me for some reason. Yeah, basically, I'll just summarize the. Oh crap. All right, yeah, but like torsion, right, is basically twisting like that, whereas bending is bending like that. Yep. If you imagine this is a beam or a rod, it's basically that. Okay. Cool. That's the last question. Sorry to those people online. I can explain that again at the end or something. All right. Cool. So that's the quizzes. Thank you. What we'll do is we'll go back over to here. I've got like a lesson plan and everything. I'll run you down on that. So that was our quizzes. We've just done that. I'm going to go over the sine and cosine rules a bit more. And then I'm going to go over supports, moments, and line of actions. Right. Then we'll take a break and then we'll dive into the questions. So today's workshop is only 3 questions. But I do want to bring up that yeah, in my Google Drive, I've added some extra questions because a complaint from this course previously was there's not enough questions to practice with. So you can go home and practice these ones. I think it's 6 questions or something. Once I get permission on Moodle, I'll upload these to Moodle as well, so you can find them on that. Okay, cool. Let's see. Just get my notes up. All right. So, yeah, I'm going to talk about cosine and sine a little bit more because they were used in lecture examples and might help understand that a bit more. I won't go over it too in depth because I guess it's from maths, like year 10 maths or something like that. So, but I'll just put in my notes because it's a good place to refer to when you're revising. So we have a triangle like this, a non-right angle triangle. Let's call the sides lowercase letters, A, B, C. And we'll call the angles alpha, beta, and gamma. And then, yeah, that just corresponds to the one across from it. So the formula goes like this. Right? Okay. So with this formula, there's kind of 2 things you can do with it. The first one is you're finding the missing side. So here's a formula for that. Right. This is kind of like ignoring these 2 pretty much. Oops. So basically that means if we don't have this information, for example, we can find we'll say you have that information or you don't. It doesn't really matter because if you have this, this, and this, you can then work out A, right? Okay. And the second one is for a missing angle. And the formula looks like that. So it's pretty similar. But in general, use the sine law when we can ignore C and gamma, is what I was saying earlier. So you can assign any of these sides as, A, B, and C. So it could be this instead. So you don't have A and alpha A, then you can use the formula that way and rearrange. Yeah, basically like that. But what I mean is when we just completely ignore one side and corresponding angle for it. All right, so there's also an ambiguous case. So this might be familiar to you from year 10. It comes up specifically when you're dealing with finding the angle case for the sine rule. Right? Okay, so say I want to find the angle alpha here. And I plug in my formula. And it gives me that answer, right? So just looking at this triangle, that doesn't quite look right because this should be an obtuse angle, so greater than 90 degrees, right? And the angle that we're actually looking for was 106.2, right? And clearly that's not what we got. So just keep in mind that the sine law, I call it case 2, you can call it whatever you want, always outputs the acute angle, right? I'll draw up y. So, oh, sorry. I was meant to include 8.7 here, right? As a side length that we knew. That's just what we plugged in here. But this is also 8.7, right? But what happened was we got this angle. We got the acute version instead, whereas we were actually looking for 106.2. Yeah. Any questions? Yeah. Okay. Cool. Next, I'll quickly go over cosine rule. So there's no ambiguous case for this one, but I've just laid it out like how we did previously for the last triangle. Formula goes like this. Right? Cool. And then similarly, there's two cases. This first one. Right? You're just looking for that, for example. And here's the second one. Let's write it out. All right. So when do we use cosine law and when do we use sine law, right? So we use cosine law when we can ignore two of the angles. So in this case, I wrote beta and gamma, right? So that's when we don't know that and that, right? Now we can work out either this or that. But again, you can assign any side to have whichever Greek letter or whatever. Cool. I'm going to check the chat. So I'm not very good at monitoring everything in the chat. So we need to remember the formula. I'm sorry, you'll have to ask Dr. Eugene. I forgot how the midterm works and how the final works. Or not that I forgot. This is like the first time teaching this course in the summer for me. So I'm not sure if you get a cheat sheet or whatever. Yeah, if you get a cheat sheet, you don't need to remember the formula. That's pretty much it. But I would go and ask Dr. Eugene about that. Cool. So next, I want to talk about moments. So I touched upon this briefly earlier. Sorry to the people online, you don't know about this yet. But moments, right? The types of moments. So there's bending moment and there's torque, right? I'm going to show this camera again. The torque is pretty much here's a beam twisting along the axis like this, and bending is bending like along the axis. I don't know how to explain it. I'll just show the sponge. It makes more sense in my head, right? I'll just do a quick drawing as well. Yeah, a classic example of torque is a wrench. So the wrench is applying a torque to the, was that, I think it's a bolt, yeah, hex bolt or something. But yeah, so that's considered torque because in order to, I guess, screw in the bolt, it has to twist around its axis to get driven into the wall or whatever you're putting the bolt into. All right. Okay. Just gonna check chat. All right, thank you very much for your contribution. All right, so next we'll talk about formula. The formula is incredibly easy. Like, it's actually the application of the formula is hard, right? The formula just goes like this. I'm just going to color it. I'll do it color coded because later I'll show you in the diagram which I draw below where all these things slot in, right? But essentially, this D part is representing the lever arm. Usually that's in meters, right? Units wise. Sometimes this is denoted with an R instead of a D or other letters, but it doesn't really matter because I mean I never write in the formula when I'm doing questions for this. But yeah. Okay, next thing to note is the units of moments in general. Generally, I like to stick to two types. So Newton meters and kilonewton meters. So keep in mind that's newtons multiplied by meters, not divided, right? I just drew the dot there because sometimes I'm lazy, I don't draw the dot. I guess it's just representing newtons times meters, right? And that makes sense because the formula, right? It's just forces have like newtons or kilonewtons, and then the lever arm is in meters. Yeah. Generally, so this isn't really like a rule so much as a trend that I noticed, but like smaller things, maybe like machines. The questions want you to have the answers in Newton meters, whereas for kilonewtons is for stuff like beams, trusses, oh, maybe not trusses. Yeah, I'll just say buildings. So civil engineers, when they're dealing with beams and columns and stuff, generally stick with kilonewton meters. Whereas some questions that I was doing in the mech school, they like to use Newton meters sometimes. Yeah. And then directions. So moments can be, so instead of moments going up, down, and left and right or whatever, like forces, moments can be counterclockwise or clockwise, right? Sometimes they're denoted with the arrow, like spinning in said direction. But conventionally, counterclockwise is the positive direction. And yeah, you'll see how this kind of plays into the questions later when we're using our equations of equilibrium. We're taking the sum of the moments. Yeah. So I don't have any questions here. Check the chat. Cool. Yeah. Okay. So here I've laid out a beam. So this beam here, call it A, simply supported beam. So call it, sometimes it's called SSB as an abbreviation, but it's basically as simple of reactions as you can get on a beam without it becoming unstable, right? So if these were two wheels, said, this doesn't resist translation, horizontal translation, right? But at the same time, if this was like a wall, and you had loading on it, it becomes statically indeterminate, which just means you can't solve it with the tools that we've been given in this course. For civil engineers, the course CVEN 2303 is structural analysis of like beams and structures and stuff like that. You'll have skills to be able to solve those in future courses. But anyway, simply support a beam. That's what we have here. But there's going to be quite a few things going on just in this free body diagram alone. If you haven't, like it's going to be maybe like quite a few things if you're seeing it for the first time. So what I'll do is, well, first I'll label what the supports are. Here we've got our pin support that I mentioned earlier. There's a roller. Okay. So let's just quickly talk about these. All right, so for the pin support and the roller support, they're going to resist some of these, but not all of these, right? So have a think about what they resist and what they don't resist. So if I was going to load this beam, what would this support kind of resist in terms of, translation and rotation? Okay, so basically the pin support resists both normal and tangential forces, but it doesn't resist rotation, right? If you want it resisting rotation as well, it would have to be a fixed support, which is like the diving board example I was talking about earlier, right? But for a roller support, it only resists normal forces, okay? And it doesn't resist tangential forces or rotation. So how I would represent this on a diagram, right? Like this. So actually what I'm going to do is I'm going to label these points A and B. I like to call this AY and AX, right? And this BY. So this is just because our beam is horizontal. So that's why I can call it X and Y. If the beam was at an angle, I'll quickly do a drawing. Maybe you'd instead want to call this, that's point B. Call it B normal, B tangential. We do something like that. But yeah, anyway, we're calling it AX, AY, and BY. Okay. Next, I'm gonna do some, question. Oh, okay. No, that's a really good question, actually. So basically with a reaction, what happens is that you can assume whichever direction you want, but then you just keep rolling with it for the remainder of the question. So what I mean is, okay, so if I had maybe like a diagonal force acting on this beam, what happens is that reaction is going to want to resist the horizontal portion of that force, right? And so when we get an X is some positive number, right? But if we assume the other direction for the arrow, like that, what's going to happen is that AX is going to be some negative number. And all that means is that it's going to be some negative magnitude. And all that means is our arrow is resisting in the opposite direction to what we assumed. If that makes sense. But mathematically, it should still work out. And if you assume this and got a negative number, there's no need to change it in your answer. You can just leave it negative and it's still the correct answer. Yeah, pretty much. Yeah, that was a really good question. Thank you. Do we have any questions from online? Yeah. Okay, cool. Let's backtrack a little. So what I wanted to show is, say we have some force. I deliberately drew it off center of this beam, right? And I've deliberately done it in red. And what we're gonna do is we're gonna do the lever arm in orange. Okay. So what I want to do is I want to take the sum of the moments about point A. Let's say I want to do that, right? And we're in static equilibrium because this beam's not moving and the support reactions are stopping it from moving, right? And so they're going to have some force in response to this external force. So, oh wait, let me give myself more space here. So what's going to happen is, because we're taking it about point A, right? And the force in question has something called a line of action. I'll just draw that. Actually, it's kind of lazy. Line of action. That's that blue bit, the dotted lines. So the line of action for a force vector extends infinitely in both directions. It's just like this invisible line. And it's going to be pretty important to think about because you're going to need to find the lever arm when you're taking moments perpendicular to it. Okay. So what I mean by that is, we're interested in point A, right? And we want to know the perpendicular distance. That's our lever arm D, right, to this force. So I guess that's lever arm there. Yeah. All right. So purposely left myself some space here because our moment is our force times our lever arm, right? For this external force. However, it's actually going to be negative. And the reason it's negative is because we're thinking about the spin that this force is causing to this point A, and it's actually clockwise. It makes it go this way, right? And because it's clockwise, and we're taking the sum of the moments with the positive direction being counterclockwise, that's our convention. We actually end up with a negative there, right? That's why that negative's there. And we're also going to have to take into account By, right? The other support, By. Let's call this distance from support to support L. So it's going to be By multiplied by L, and it's going to be positive. It's going to be positive because this arrow causes a counterclockwise spin on point A, right? So, and now we've actually got this equation which we can solve for. Typically, when we have when our force is given in like an actual number, not like the letter F, we can actually solve for what the support reaction By is. So another thing to keep in mind is that when we took the moments about A, notice how that point in particular passed through two other vectors, right? AX and AY. And so the lever arm for those was actually 0. So mathematically, we can just completely discount any force vectors going through the point that we're taking our moments about, right? That's why it kind of works out. If we took the moments about B instead, right? So now we're looking at this point here. If we decide to do that instead, okay, well, I didn't prepare notes for this one, but basically, that distance there is L minus D, right? Because the length of the beam minus the lever arm, which we specified before. I just didn't want to call it a different symbol, right? But it's going to be positive because it's causing, this force is causing a counterclockwise spin on point B, right? And AY, right, inversely is going to be negative because it's causing a clockwise spin. Anyway, I think you get the point. Chat. Okay. I'll zoom out. Okay, sure. All right, yeah. Cool. Does anyone have any questions with that? No? All good? Okay, cool. So that's kind of the theory behind it. I know there was a lot. We'll move on to the questions after we take a break. But yeah, everyone can take a 5 to 10 minute break. What I'll do is I'll put up the attendance. So make sure to fill that out because the attendance form will like not be accepting any more responses after the tute's over. So yeah, take the attendance or fill out the attendance form. People online as well, please. Yeah, but feel free to get like water or go to the bathroom or something. Oh lol. Okay. Give me a second, I'll sort this out. All right. Can you guys try now? I think it should be back open. Yeah, if anyone has any questions, feel free to come up the front or something. Oh, so okay. Basically, I'll send a link to you through that email after the lesson's over. I'll just have to go home and send it to everyone. But if you were here last lesson, or for the people who were here last lesson, I sent the same folder to everyone. So everyone who was here last lesson has a link already, but it's the same link. Yeah, I would tell you to look at Teams, but I think Jing only made the team like today for today's workshop. The Teams meeting for yesterday's workshop is like a separate meeting, so I'm not sure if you can access that anymore. But yeah, did you have problems viewing the recording for yesterday's lesson, or like, did anyone have problems with that? Yeah. Sir? Wait.
Viewing like a recording.
Yeah, yeah.
It's like on an access.
Yeah. Yeah, like I'm still trying to work out how to use like Office Suite for sharing. Always Google Drive. I think there was a few people who sent like requests to me through my email, like when they requested access. I've tried to let people like through, like as many people through as possible, but it's still a problem. Just feel free to reach out to me via Teams or whatever. So that was a problem for like the first workshop recording. And if it's still a problem, I'll try to upload it to Middle. But yeah, hopefully there's not going to be a problem for this workshop. Yeah, that's fine.
It's just that it's easy, so it's gonna be every like every lecture up until Wednesday. Wednesday. And because it's I think yes in Wednesday's lecture it says from 6 to 8 next Friday. So is it online? Or house?
So there's just some things I'm actually not so sure. Sorry, so the stuff like that, it's best to ask Dr. Eugene specifically for assessment relays thing. And there's another demonstrator who does the labs. I'm not the guy who does the labs. So when you have lab questions, you can ask. Sorry, I was going to know. Thank you. Lectures count towards assessments. How do fixed supports and rotations? Yep. Okay. Still not on the terms. Oh, what about sort this out later? Right. Cool. All right. All right. So basically, yeah, probably saw it on the board there, but just answered a couple of logistical questions. So, could you stick your hand up if like you're having troubles joining the teams? Like you're not on the Microsoft Teams yet? Couple of people. Okay. Because I actually like I think I was directly invited to join the teams by the lecturer. So I don't know if there's like a link on Moodle that you're supposed to click to join it, or so people directly get added, right? Okay. So if you're having problems like in terms of you haven't been added to the teams, try to please send Dr. Eugene an email, and she'll add you probably as soon as possible. And then maybe in the email you can talk about the attendance thing as well. If like you missed like a lecture, because you were, yeah, like say you missed today's lecture because you haven't been added to the teams yet and you couldn't attend on campus. Oh wait, no, it's only online, right? Yeah, then yeah, just include that in the email. The other thing to note is that the 90% attendance thing doesn't count. Like yesterday's lecture and workshop doesn't count towards that because a lot of people didn't know it was happening. So yeah, she's excluded that. I believe lecture attendance is part of that 90%. I want to say, yeah, just from the wording of what she sent in that message. So yeah, check. Yeah, a lot of people were directly added. So yeah, if you haven't directly been added, just shoot her an email. There should be, I think the majority of people have been added directly. So yeah. Okay, cool. So we're going to continue just by doing the questions now. There's only 3 questions, so it shouldn't take very long, but we can kind of take our time with this. Sorry, I'm just getting my notes up. All right, cool. So what I've done is I've just drawn a free body diagram representation of the question. I haven't drawn everything in yet. We still have to draw the external loading or the forces. But what I've done is I've gone out and drawn the support reactions already. So here, this is like some kind of rocker, but it's effectively a roller support because the idea is that it doesn't resist the horizontal translation, right? So when I said there's 3 main types of supports, what I mean is mathematically there's 3 types of supports because there's just variations of the same thing, right? And here's a pin support, right? Yeah, so if I drew these properly, it actually does have like a little hinge connecting the member and the support looking thing. That's actually a little hinge. But yeah, anything else to talk about here? No. And what I've done as well is I've just included the distances in meters. Okay, so basically we have a point load here, right? We're going to consider this box a point load. And we've also got a distributed load, which we're going to we're going to denote this with W. Oh, actually, sorry, I'm drawing this a bit lazy. Let me draw this properly. So what it actually looks like is this, with like the downwards arrows, right? So I drew it like that because that's like the shortcut notation for a uniformly distributed load. So what a uniformly distributed load is it's basically a load that's spread out. So the example that I like to give is imagine quicksand, right? And you just hop into quicksand and like, you just jump and your feet go straight in, and you can consider that like kind of like a point load acting on the quicksand. But if you had a surfboard and you did the same thing, and you put surfboard down and you jump on the surfboard, your load, right, same amount of mass is distributed, right? In that case, it's distributed maybe over an area, so in 2D, right? But when we're talking about a beam, we want to analyze it as a 1D rigid body. So this distributed load, the units for it, we're going to see, it's going to be kilonewtons per meter, right? So it's spread out linearly over a linear distance. Okay. Whereas this is just going to be in kilonewtons units. That'll hopefully make more sense in a second. So let's do the box first, right? So we've denoted the box's point load with P, right? And it's 300 kilograms times 9.81. And this comes from mass times acceleration due to gravity. So this is 2,943 newtons, right? Which I don't know, this is a preference thing, but I'm gonna leave it in kilonewtons because we're working in the scale of beams, so I prefer kilonewtons for this. Okay. So before we tackle the uniformly distributed load, let's quickly talk about the units. So the units of newtons, right? It's kilograms multiplied by meters divided by seconds squared, right? Let's keep that in mind for this bit, because how the question's worded and why we need a uniformly distributed load to begin with is because it says that the beam has a mass of 50 kilograms per meter of length. Okay. So what that's going to look like when we calculate it is 50 kilograms per meter, right? Multiplied by 9.81 meters per second squared, right? That's the acceleration part. But the difference is when we put this in the calculator, the units are going to be in newtons over meters. Cancel everything out. Okay. And say I want to do everything in kilonewtons again. So then this becomes 0.4905 kilonewtons per meter. So yeah, again, so this is our point load. So we're looking at. And this is our distributed load. And that's going to be a force over a linear distance. Yeah. So in terms of this unit, this is actually kind of a weird concept. Like, you haven't seen distributed loads yet, but you'll see it a lot next week. So I think on Friday you're going to be having the lecture on trusses. Then we're going to solve trusses. Trusses won't have distributed loads, but once we start talking about the analysis of beams and like shear force diagrams, bending moment diagrams, that's next week, right? That's when you're going to see distributed loads come up a lot. And what I was saying before uniformly distributed loads, because there's going to be more types of distributed loads. There could be like a triangularly distributed load or something that looks like that or whatever, but we'll get to that later. But yeah, this is just kind of like an early introduction to the topic, to the concept. Yeah, I think like for those of you who missed it in like the end of yesterday's workshop, in the early weeks of this course, they kind of just sprinkle in stuff that's from later in the course because I want a variety of questions, but like you literally haven't seen it yet. So like, yeah, anyway, whatever. We're gonna keep going with the question. I'm gonna quickly check Teams. Yeah, it's fine. Okay. All right. So essentially, here's the second step. We're going to solve for the support reactions using equations of equilibrium, right? Sometimes it's called EOE as an abbreviation. Okay. So when I'm talking about equations of equilibrium, what I'm talking about is some of the forces in the x direction is equal to 0, some of the forces in the y direction is equal to 0, and some of the moments is equal to 0 as well. And the moments have to be taken about a certain point. Okay, just keep that in mind. So yeah, you always need a reference point for the moment calculation. Yeah. So we'll see how that plays into account later. Okay. So, oh, okay. So I'm going to have myself. So this is point A. This is point B, right? So okay, have a think about this. Would you rather take the sum of the moments about A or B? Yeah. Yeah. All right. I like the way you think, but in this particular case, it actually doesn't matter. It was kind of a trick question. I'm not gonna lie. Sorry, I switch you up. But like, the reason it doesn't matter is here. I'm gonna get you to think about the lines of action. So I'm gonna do it in like this highlighter color. So what I'm talking about, the lines of actions. What I'm going to highlight is just the lines of actions for our unknowns, which are support reactions. Okay. So we basically want to choose a point which eliminates every line of action except one unknown line of action, right? So if we take A, what we're going to do is we're going to end up solving for B. By rather. Okay. And if we take the sum of the moments about B, we're going to end up solving for AY, right? That's the way you kind of want to think about it. It just happens to be that regardless of whichever point we choose here, A or B, AX is just going to line up, like overlap with it anyway. So you're not going to need to solve for that when you're taking the moments, right? Okay, so we're going to take the moments about B. For a second. I'm just going to copy this over temporarily. All right, so we're looking at point B here, and AY is going to cause a clockwise moment, right? So it's going to be negative. And the lever arm is 3.6 because 3.6 is 2.4 and 1.2 added up, right? Okay, here's where it gets funky, right, with the distributed load. Okay, so for a distributed load, in order to solve for support reactions, and when we're accounting for this distributed load, we want to find the middle of the distributed load and pretend that the entire distributed load becomes a point load and we take the line of action from there. Okay. So we solve this to be 0.4905 before, right? Kilonewtons per meter. So essentially, we know it acts over 3.6 meters, right? So now we have the magnitude of this resultant arrow. Maybe I'll do it in purple. What was essentially done is we've pretended the blue part is now the purple part, right? The purple part would be 3.6 times this, right? And now we also want to find the lever arm and multiply it, okay? And so the lever arm is going to be in the middle of the beam to point B, right? That's going to be 3.6 divided by 2, right? It's getting messy. So now we've accounted for our distributed load, okay? And keeping in mind that our distributed load is pointing downwards and thus causes this counterclockwise spin. So it's positive. Okay, next we're going to do our point load, right? So similar thinking. What we're going to do is multiplied by the lever arm, right? And that's just this part here. So lever arm's 1.2. It's going to be a positive moment because there's a downwards force and we're taking it about point B. P was 2.943. So I'm going to delete this a little bit. Yeah. I'm going to check for anyone talking in the chat. For distributed loads that aren't uniform, is it a similar process? Find the center of mass and then pretend it's a point load through center of mass. Yes, we'll get into that next week. So for a triangularly distributed load, right, what I'll do is I'll just give you a sneak peek. A triangularly distributed load, its center is going to be 1/3 from the big end, or 2/3 from the little end. Right. So that's where you're going to pretend that the resultant arrow is, say, triangularly distributed load. I'll leave that in the corner if anyone wants to copy that down, but I'm going to delete that later. All right, but essentially, we've just got that one unknown now. So we rearrange for it and solve for it. This. Right, so now we have AY, it's all good. Yeah, so looking at our free body diagram, right? We've got AY. Now we don't have BY and we don't have BX, right? So you can actually solve these in either order. You can also have solved BX in either order because there's actually no horizontal loads acting on this beam. There's no horizontal external forces, and therefore we actually already know that the support reaction at BX is going to be 0, but I'll do the calc for that anyway. Yeah, so this would be a different story if we had a diagonal load like that, right? So if it was a diagonal load, then yeah, there would be some like horizontal reaction that's resisting it, right? But that's not the case. Okay. I'm gonna delete this now. Is that all good? Yeah. All right. So what we're gonna do is we're gonna take the sum of the vertical forces and so we're gonna solve for BY essentially. We've already done BX now. So AY, that's the first one, and then BY. and then minus the distributed load multiplied by its run, so 3.6, right? So what that's done is given us the magnitude, the resultant magnitude of that distributed force over that the length of the beam, minus P, which is the point load, right? So we're going to substitute this with the numbers that we know. And now we just have By, which is unknown, which we're going to solve for. That gives us By. There we go. We've got everything. Sorry, I'm just going to mute you real quick. Do we have any questions? No? All right. Do we have any questions in the room? No? All good? You're good. All right. Cool. We'll move on. All right. So here we have a trailer is towed in the forward direction and the force is applied onto the ball of the trailer hitch. Determine the moment of this force about point O, which is over here. Okay. So there's actually kind of two ways to look at it. We're first going to look at it as like a resultant moment, quote unquote, question. All right. So that's what we're going to do first. All right. So first, this is kind of optional, but I'm just going to simplify the question a little bit. I'm going to break the force F into its X and Y components. Okay. So that's Fy and Fx pretty much that I want to solve for. So yeah, from last workshop, we basically just get the magnitude of the diagonal and sine or cosine the angle, right, to get its horizontal or vertical components. So it's 500 newtons. And all right, is this going to be sine or cos? Have a think about it. Or the x, the horizontal part. It's going to be sine. And it's because it's not the butterfly angle that I was talking about last time. Yeah, it's sine because it's the opposite of the 30 degrees, which is going to be horizontal over there. What I should probably also do is make that negative. My bad. Right. So it's going left. So I'm just going to call it. You know what? Because I've drawn the arrow left, maybe I should just do this. Yeah. That's basically what we're talking about. So Fy is similar, but we just change it to cos. Okay. Yeah, so now we're just broken it up. And why this is kind of like why I'm doing this, right, is because I'm gonna take the sum of the moments about O, and sometimes it's useful to break it up into these forces because the lever arms, yeah, because we're given the lever arm in terms of 38 mil and 275 mil, right? So if we just break it up into this horizontal and vertical component, it's actually going to be easier to get the moments, right? But sometimes, if they give you this distance, right, the perpendicular distance, right, it's actually a bit, like easier just to leave it as is. Do you know what I mean? Because, yeah, anyway, it depends on the question. There's not really like a set rule for it. And you just do enough questions and you kind of figure out a pattern. Anyway, so got the result in a moment. So this is similar to what we did last workshop on resultant force, right? Except we're gonna do resultant moment here. So what that's gonna look like. Let me zoom out. Let me delete that. The sum of the moment's about 0.0. We're going to equate that to our resisting moment. Oh, sorry, our resultant moment. I'm just going to leave it in newtons and millimeters and then convert it later. So we're looking at 0.0, right? And fx, right? So this part is 250, right? And here's his line of action. And the lever arm is 38 mil, right? It's causing a counterclockwise spin, so it's going to be positive, right? And then, yeah, the Fy is also going to cause a counterclockwise spin, so we're going to leave it as positive. And its lever arm is 275 mil. This gives us this. In Newton millimeters, right? Oh yeah, so question. Oh, like, yeah. Normally I do. I don't know why in my solutions I decided to convert it later. I normally keep the lever arms in meters. Yeah. Is anyone a civil engineer? Yeah. Like, maybe chuck your hand up. Is that are you doing like 2400 mechanics of solids next time?
Yeah.
Yeah. So when you do mechanics of solids in the next course, right? And you're going to be analyzing like the cross section of the beam, right? These dimensions are actually more advantageous to keep in millimeters. And then when you do calculations on a cross section on a beam, for example, in that case, you want to keep everything in newtons, millimeters, sorry, newtons, millimeters, and megapascals, because these units convert perfectly with each other. But yeah, in this course, I find it like pretty useless to keep things in millimeters in general. Yeah, that's kind of random. I'll keep that off to the side. Let's copy that down. Oh yeah, let me just convert this. Can you tell I'm a civil engineer? I'm only going to give examples from civil engineering because unfortunately I don't have enough experience in like mining and mech and other stuff to give examples or as thorough examples for those ones. So yeah, I'm going to check the chat over here. Wait, what? Okay, sure. All right. So yeah, that's basically the resultant moment kind of. I'm going to delete this, right? That's like the way you think about it in terms of like resultant moment, except if you look at like after this workshop, right? We're gonna like release the solutions for this question. The way they do it is a little bit different. And what they do is they effectively consider this as a fixed support, right? And they give this OY, OX, and MO. So that's a resisting moment. So they treat it like a reaction kind of question. And when they take the sum of the moments about O, what that means is OY and OX, those ones will have like a lever arm of 0. And so we're just solving for MO. So look, something like this. So the moments 0, MO plus, all that stuff, right? But then when you solve for MO, you will end up with a negative version of our answer. Okay. And so all that means is that instead they solved for what the support reaction would be given our external loading. But what we solve for is what is the resultant external load. If that makes sense. So what we solve for is kind of like what the external forces do, and then what they solve for is what the kind of resisting internal forces are doing. If that makes sense. So this is that's why they get the negative number. So yeah. Yeah. All good. All right. Sorry, last question. Then you'll be out of here. All right. Okay. So here we have also kind of a weird question. It's essentially saying that there's like this hammer and it's being like pulled with a force of 200 newtons here, and it's pivoting on this corner, and it's pulling this nail out. So there's like a bunch of random stuff going on. Okay. But they essentially consider this a pin support for the hammer because it's free to rotate, right? But it's normal and tangential, or like the x and y. Here we saw it as x and y. Those reactions are resisted, right, by the ground, right? And additionally, they call the tension in the nail T. And it's going down. So this kind of looks like the question that we were doing yesterday, with the spike in the wall. Yeah, it's essentially like, I don't know, it's like solved a bit like a roller support, but it's not a roller support. I don't know, it's just like this unknown. The nail, yeah, can only go in and out of the wall. Actually, it's the opposite of a roller. Can only go in and out of the wall. So yeah, anyway, sorry. That wasn't the best explanation. But that's how we've set up our unknowns, okay? And yeah, so you want to find T and you want to find A, X, and AY. So essentially, you can solve it like a beam, weirdly enough, because it's simply supported. Because this is kind of solved like a roller, right? The T just has, yeah, whatever. I'll just solve the question. All right, let me redraw that here. Okay. All right. So the first thing I'm going to do, take the sum of the forces in the x direction, okay? And here we actually have this diagonal loading, so there will be some horizontal resistance, right? Reaction, and that's going to equal 200 cos 20 plus AX. So that's just the horizontal component of that force, plus AX, right? So we assume the arrow in the right direction, but when we solve for it, we're going to get a negative number, right? Yeah, because of kind of what we were talking about before. You can assume the arrow in any direction, and if you get a negative number, it just means that your reaction is actually acting in the other direction to what you assumed, right? That's fine. So we just leave it as is. All right. So next, right, do you take the sum of the moments about a point, or do you take the sum of the forces in the y direction? I think. So if you take the sum of the forces in the y direction, you're going to have two unknowns, right? So you can't do it straight away, right? So that's why generally you have to take the sum of the forces in the y direction when you're solving for a beam. This isn't a beam, but when you're solving for a beam, before you take the sum of the forces in the vertical direction. Okay, so that's exactly what we're going to do. So we're going to take it about A, right, to solve for T. So T is 50 millimeters away, and this time I've decided to convert the lever arms to meters straight away. let's do it like that. And same with this one. Oops. Right. Because you can think of it like this. Sorry. So basically, we have this diagonal force, right? But they straight up tell us the lever arm, so we don't need to split it up into our horizontal and vertical components. Right. Now we can solve for T. It's 800 newtons. Cool. All right, and now since we know T, we can solve for the sum of the vertical forces. Okay. Let's have 800. Okay. So technically, could we have solved this question by taking the sum of the forces at A, and then taking the sum of the forces? Actually, it's kind of a bad question to do it on because they don't give you the distance there. Okay, you know what? Ignore that thought. All right. Lastly, the question asks for us to find the magnitude A of the force exerted by the hammerhead. Yeah. And what I've also decided to do in my calcs is find the angle from the horizontal. So the way you do that, just a recap from last lesson, you just use Pythagoras, find the magnitude. Right. That gives us our magnitude. What this might look like, if we draw it out, is AX look like this, AY looks like this, and FA is our diagonal resultant force. Okay. What we can do is we can solve the angle as well, down from the horizontal. So that would be theta is equal to tan rise over run. Yep. That's our question. Well, what's going on? Yep. So anyone have any questions in the room? Mine as well. Could you please explain the tension part again, please? Can you show question 2? Okay. Okay. So for the tension in the nail, it solves similarly to a roller support, but not for the same reasons. So for a nail, it can only go into the wall or be pulled out of the wall, right? So you wouldn't draw the tension in a nail. You wouldn't draw it like sideways, right? You wouldn't represent it like that. So yeah, you can think of the tension in the nail as an unknown that's going into the wall. I think that's the best way I can put it. And then regarding showing question 2, I might just delete this. It's kind of irrelevant. Question 2. Yeah. Oh, do you have a question?
So, it was the distance between the block and the grid, 45 millimeters. That wasn't really relevant to the question. So, was that like just like something throwing you off?
Yeah, it might have been. Let's have a look at that.
When you solve it, you use the 15 millimeters to find the moment between T. Use the 200 meters, but you don't ever use a height of the block itself. So is that usually happen with these questions? Like that detail just throw it off?
So, okay, I'll just explain over here for the people online. So the question in the room was, in question 3, why was that 50 mil like not used? This one here. Oh, sorry, 45 mil. Yeah, sorry, yeah, you're right. So basically these questions are from the textbook, and the way that I source the questions is from the Mech School, which just like they take it from the textbook. So it's all written kind of by the same author. 99 or like 95% of the time, they don't include unnecessary details. I guess this is an exception though, and that's a good spot. Yeah, I don't think you ever use that. But most of the time they don't throw you stuff that you don't need to use, I'd say. Yeah. I guess like no, there's no reason to use that. Yeah. I guess it's like if people like originally tried to break this up into the horizontal and vertical components first, it would be hard to calc though. But yeah, anyway, maybe it's used then. I'm not too sure. Yeah, you're all good to go, by the way. Thank you. Thanks for going. We see the bottom of the last page again. Oops. All right. I'll stick around for a bit longer if anyone has any questions, but otherwise everyone online is free to go as well. Thank you. See ya. Might stop recording.
Well, there you go. Is there a way to like I log into the meeting